Hola a todos, bienvenidos a este increíble evento. El día de hoy estoy muy emocionado de tener la oportunidad de presentarles a una persona muy interesante. Su nombre es Dario Tranchitella y el día de hoy nos viene a presentar una conferencia la cual se titula KubeInception, Running Up to a Thousands Cluster in the Real Cloud Native Way. Ok, Dario, es un momento.
Mucho gusto, Luis. Mi nombre es Dario. Yo estoy estudiando lo español because I'm Italian, and I'm really sorry because I need to translate. Sometimes I need to switch the language from Italian, English, and Spanish. Anyway, I'm really happy to be here, although virtually. So we can start with the video. Hola a todos, mi nombre es Dario Tranchitella y gracias por atender mi charla. So, I'm not Spanish, I'm Italian, I'm just trying to learn more your awesome language. So, thank you so much for attending my talk. And today we are going to talk about Kamaji and how to run 1,000 of control planes in the cloud native way. So, we got some slides here. I hope that you can see that properly. And before proceeding, I want just to briefly introduce what I'm doing at Classics. I'm the CTO, and we are the leaders, according to us, about multi-tenancy. And I'm going to explain you why we are talking about multi-tenancy. And we got this nice slide that I always show during the meetups, the conferences, because if you think about the infrastructure, since we are working with Kubernetes and the cloud, essentially you got your own servers, and these servers are partitioned, and these partitions are used by multiple tenants, such customers or end users, and so on and so forth. And it's pretty similar to what you have essentially when you are creating virtual machines from Blade, so from the on-prem servers, but even on the cloud. So with multi-tenancy, essentially you can increase the optimization of your resources, you can control the resources, and also isolate to offer a seamless offering of cloud services. And if you think about Kubernetes, essentially it's pretty similar because you have the namespaces, and you need to create virtual machines, and these virtual machines are going to host workloads for your customers. So with that said, keep in mind that multi-tenancy has multiple models, and I'd say it has multiple shades of gray. But today we are going to talk just about the hard isolation. So we are not focusing on namespaces, but rather having multiple clusters. Why that? Because in the end, if you think about that, when you are creating your cluster, you want to be sure that just your own workloads are going to run there. So you need your own separate cluster. And we need that this approach is pretty common because you have hard isolation. Is much more easier to understand because you're bringing your virtual machines, you go to control plane, you install your other components, and so on and so forth. But from the operational standpoint, so like the site reliability engineers, so the infrastructure people, is really cumbersome, mostly because you need the operational excellence. You need to be very good at managing Kubernetes. And also, you have to provide best performances and at the same time containing the cost. And last but not least, also, you have all the troubles of running a fleet of Kubernetes clusters, and that could be really cumbersome. It's pretty common right now having multiple clusters, but having just a few is not so much cumbersome as having dozen, hundred, or even thousand of Kubernetes clusters. So you can imagine the pain, and we are going to get through it, don't worry. So what are the challenges in running multiple clusters? I would say that the first issue is that we know that unless you're using a managed service, you need free virtual machines for the control plane. So the control plane is hosting all the data like etcd for your cluster. There is the API server, the control manager, but since etcd is based on the Raft algorithm for the consensus, you need at least 3 virtual machines. So it's expensive. Then you have to control and to manage the control plane. It's our part of the job, we have to be sure that Kubernetes is always up and running, and obviously you have to perform monitoring, maintenance, and so on and so forth. Like rotating certificates or the CA, although the certificate authority should last, something like 10 years. And then you need to be sure that the API server is always up and running, ensuring high availability. and you need to perform upgrades, so a lot of tasks. So it means that you need people, and people. So the one cluster per tenant is pretty common because in the end you're ending up with multiple clusters. So all the tenants, all the users are pretty happy, but the issue is that you got a linear exponential burden. So what does it mean? It means that more cluster you have, more work is up to your department. And also having multiple clusters brings multiple issues like the governance. So you need to be sure that all the clusters are updated and patched. And also you can get the issues. I'm not saying it's gonna happen, but the problem is that you need to be sure that the control over the cluster is always controlled by you. And furthermore, since we are talking about people, the people, they don't scale. It's really hard to maintain. Just to try to explain you what's the outcome, I prepared a meme. You know, I'm a meme master, at least I think so. And this is essential, this is from my standpoint, what's happening when you have a team that is demanding a lot of clusters and you are in this department of the scalability engineers. So essentially every time you need to create one cluster, besides the provisioning, it's all about you in maintaining these clusters. And furthermore, this is another meme because I'm a huge student fan. So you can imagine what's going to happen if you have multiple clusters. So it means that also your on-duty calls are going to be much more burdening because obviously we are not putting all the eggs in the same basket, pretty sure. But the issue is that more clusters means more maintainability from your side, more maintenance. So besides that, also running multiple clusters is bringing some other downsides like the control plane tax. As we already talked, it means that you need at least 3 virtual machines. And furthermore, you need more time to maintain these clusters. And as I said, trying to recap everything, the technology scales because right now creating cluster is pretty straightforward. Everybody is able to create their own clusters, but the problem is that since we got the technology that is scaling out, people cannot. Unfortunately, or likely, it really depends on your standpoint, we cannot do kubectl scale, site reliability stuff, replicas 10, 20, 30, 50, or 100. So it means that we need to find a new way to manage such scenarios where you have a fleet of Kubernetes clusters. So that's the reason why I would like to introduce you for the hard multi-tenancy Kamaji. So Kamaji is the second open source project that we developed at Classics, and its name is coming from the Spirited Away anime movie from Studio Ghibli. And essentially the analogy here is that, I don't know if you ever watched Spirited Away, you should do that. The boilerman here is providing the hot water to the bathhouse, to the guest. And essentially Kamaji is doing the same by providing control planes. So you don't know all the internals, but you're consuming something as a service. And the same applies also with Kamaji. So I would like to get through all the main features of Kamaji, and we can try to elaborate a bit more. So the first thing is that with Kamaji, we would like to offer a self-service Kubernetes. Self-service is the buzzword if you would like to adopt multi-tenancy in your organization. You don't need to open a Jira ticket asking, please provide me a Kubernetes cluster. So in the end, you should be able to create, obviously, according to a set of policies and rules, your own Kubernetes clusters. Second, we got also the need to get cheaper control planes. We already talked about the fact that Kubernetes control plane, especially for small size clusters, could be cumbersome. The control plane must be always up and running, otherwise the worker nodes will be headless. So the control planes with really virtual machines is really complicated. So we need to increase the density of our control plane. And Kamaji is addressing that in a different way compared to virtual machines, because we are running the KubeInception, like the movie. So we are running Kubernetes inside of Kubernetes. So it means that we are taking full advantage of the operator pattern, because we are treating the Kubernetes control plane as a sort of application in the management clusters. So we are getting out of the shelf automation, our constant reconciliation, self-feeding, migration, and all the commodities that you can have from a managed service. Furthermore, with Kamaji, you can create a multi-cluster management out of the box because you have this management cluster which is offering self-service capabilities to the developers, and you have this single entry point to manage the whole infrastructure, or rather I'd say the whole Kubernetes platforms that you are maintaining. And furthermore, you are leveraging on multi-tenancy. So multi-tenancy is a way to increase the density of your resources and at the same time also ensuring that the resources are not stepping on each other's foot about CPU, memory, but furthermore about the data, because everything is running into Kubernetes. So it means that we need to be sure that the data is not compromised, no privilege escalation is happening, and we are going to see how we are achieving that inside of Kubernetes along with Kamaji. And last but not least, we are not running yet another Kubernetes distribution like K3s, K0s. I don't have anything about that. But if you think about that, I want to provide Kubernetes vanilla. So it means that I want to run plain Kubernetes and I can install whatever I want on top of that because I am the platform administrator, and maybe I'm going to pick a dedicated and selected tool suite, tool chain about the monitoring and so on and so forth. So it's going to be totally vanilla, totally upstream. So you have all the requirements to build something on top of that. So Kamaji is totally unopinionated on that approach. So let's try to get deep in more depth about the architecture of Kamaji. As I told you, essentially Kamaji is running as an operator, so it must be installed in a management cluster as an operator, and we are leveraging on CRDs, custom resource definitions. So with that said, essentially we are making some objects, some domain objects as first-class citizens in Kubernetes, and these two objects are the tenant control plane, which is the one object that is creating our Kubernetes API server, and then we got the data store. So what is the data store? When we are talking about data store, we need to think about etcd. So it's the backend where we are storing all our values. So let's try to see a diagram about the architecture. So as I told you, we need a management cluster. We call that in the Kamaji jargon the admin cluster, where we can spin up multiple control planes, and these control planes are running as regular pods in the admin cluster. And you see here that we got the control planes, and then we got multiple multi-tenant data stores. And you see here that we can support etcd, PostgreSQL, or MySQL. Don't worry, we are going to talk about the data store. And after that, we got the tenant clusters that are essentially made of just worker nodes. So it's pretty similar to what you can have on AWS. Essentially, you got your own virtual machines running in your AWS account. It could be AWS, vSphere, Equinix, OpenStack, it doesn't matter. And then you're consuming the API server as a service. So it means that essentially you cannot break your own control plane. You're consuming that as a service because it's externally managed by Kamaji. And this is very important because the most cumbersome stuff, the most cumbersome task are managing control plane, and if you're a developer, you just want to focus on shipping your own applications. So this is the architecture of a control plane, and you see here that essentially we are running as pods, and in this pod we are running the API server, the controller manager, and the scheduler. Then if you think about these three components, essentially they are stateless. They don't have any state because the API server is just an API server connecting to the etcd, or rather I should use the data store concept. So the API server is connecting to the multi-tenant data store, and what is exactly? So a data store is an etcd with a multi-tenancy enabled. So it means that one etcd cluster can host multiple data of multiple clusters. The idea here is to say instead of shifting the multi-tenancy to the infrastructure layer, so using virtual machines that are really cumbersome to manage, what we can do is to orchestrate everything at the Kubernetes level and moving all the data into multiple multi-tenant data stores. So what I can have is multiple customers. Each customer is having their own clusters and grouping together these clusters data into one etcd instance, or rather I should say data store. So the idea here is to combine, to compress data together in order to decrease the pressure on the site reliability engineers, because otherwise you will end up with 8,000 control planes and 1,000 of etcd clusters, and it's not really efficient if you think about that. So these are also the technical standpoints about Kamaji. So we got the operator. We saw that the control planes are essentially pods running in these management clusters, and the worker nodes are joining these control planes just as regular nodes, but the control plane is totally hidden from the end user. So it's like EKS or AKS. And we already talked about the data stores. So with the data source, I'm always, for the sake of simplicity, referring to etcd, but keep in mind that with Kamaji, you can use MySQL, you can use PostgreSQL, so it doesn't matter because we integrated that with a project that is named Kine. So Kine, K-I-N-E, is the etcd shim that allows to use a different backing data store for your Kubernetes clusters. So instead of using etcd, that has some limitations, especially when running at scale, what you can do is to use MySQL, or rather PostgreSQL, and shifting the multi-tenancy to a different layer. So what you can have is having one schema, so one database for each customer. And PostgreSQL is working very well, especially at scale. It offers systems for data replication, backup and restore, and partitioning is very, very efficient. So if you're planning to run at scale, I would suggest you to give a try to Kine, that is already used by K3s, by the way, and also to PostgreSQL. Last but not least, also we got connectivity, and connectivity is one of the most underrated projects in Kubernetes because it's really important to use that if you have your worker nodes that are outside of the control plane network. So with connectivity, essentially, we can bring multi-cluster management on multi-cloud providers. You can imagine the control planes hosted on premises, maybe with their own IPs, and then the worker nodes joining these clusters using connectivity, although they are on a different subnet and maybe they don't even have a public IP. It's really, really powerful. I would suggest you also to watch some nice talks from the latest KubeCon about connectivity. So let's try to focus on our talk. So with Kamaji, essentially, we are entitled to run control planes in a management cluster using CRDs. And we have also introduced another tool that is Cluster API. So Cluster API is a project really, really interesting because it brings the declarative approach to create multiple clusters on different infrastructure. So Cluster API is a sort of contract where you are defining your cluster specification, and according to the underlying infrastructure provider, you can get it deployed everywhere. So you need to install Cluster API, then the provider, and adding all the required information like, I don't know, the OpenStack security groups or the vSphere, OVF ID, and so on and so forth. And essentially, Cluster API is creating on your behalf all the clusters. So it means that essentially it performs all the dull tasks like creating virtual machines, scaling virtual machines, joining them, and so on and so forth. We are going to have a sort of demo. So keep in mind that now I'm going to change the focus here. You should be able to see my terminal, and you see here that I have this cluster. So kubectl version, I am running 125. Should be this one. Client version? No, the version, the server 127. And I already have also some providers. So kubectl get providers for the Cluster API. And you see here that I have Cluster API, the in-kube infrastructure, and I have also the control plane Kamaji. So this talk is not going to focus on the on cluster API itself, but rather I just want to show you how much is easy creating your control plane with Kamaji and get it combined with cluster API. To show that, we have some manifests, and these manifests are placed in this file. And you see here that essentially we got this definition of the cluster, and the name of this cluster is going to be copy quick start, where we can define all our cluster network configuration. And please take a notice here about the infrastructure reference, because we are running everything on KubeVirt. KubeVirt is a nice project, but it could be AWS, it can be Equinix, vSphere. It really depends on your infrastructure. Right now I'm running on KubeVirt, so it means that I'm creating virtual machines managed by Kubernetes. So it's much more extreme, because we are having this management cluster that is hosting control planes and then creating virtual machines. So really mesmerizing. But I just want to focus on this one, so Kamaji control plane. With the Kamaji control plane, this is a resource that is creating the control plane that is going to be used by cluster API. And this is going to be converted into the tenant control plane custom resource definition managed by Kamaji. But as you can see here, we got our cluster, then we got our control plane, where we can have multiple information about the control plane, like the cgroup FS driver for the kubelet, how it must be exposed, the API server using internal IP and then the external IP, how it must be exposed, and also the replicas and the version of Kubernetes itself. Then finally we got the machine template for the KubeVirt that are going to create the virtual machines managed by cluster API, and as well the kubeadm configuration template. Keep in mind that Kamaji is sticking to the kubeadm bootstrap process, so it means that it perfectly integrates with cluster API. So after that, finally, what we can do is to deploy this cluster. So what I need to do is to issue kubectl apply -set tnp kubevirt, and we will see that we are going to have multiple resources created. Just for the sake of having everything crystal clear, I'll issue also clusterctl describe cluster copy quick start. Obviously, it's not found, but once I issue the apply -f, you will see here that all the objects are going to be created. As you can see here, we are waiting for the control plane, because Kamaji is creating control plane on our behalf, and you should be able to see here that just in a matter of seconds, the control plane will be up and running. In fact, if I issue kubectl get deployment, you will see here that we got this control plane copy quick start kubevirt, and we got our control plane running as pod. In fact, if I issue kubectl edit pod this one, you will see here that we got in specification our API server up and running. This is managed by Kubernetes itself, so it means that, well, by Kamaji. It means that if I have this deployment copy quick start kubevirt, if I delete this one, it's going to be created back by Kamaji. And in a matter of seconds, you should be able to see here the control plane being up and ready again. Here it is. So, during this demo, we saw that essentially the control plane was able to be created in a matter of seconds, and there is a constant reconciliation. Like any regular application you can have on Kubernetes. So essentially the idea here is to reuse the same machinery that we have with Kubernetes applications, but apply to Kubernetes clusters. And cluster API is really helping here also about the virtual machines, because Kamaji is just focusing on the control plane. The worker nodes can be managed using cluster API or your preferred automation like Terraform, Ansible, Cloud Init, and so on and so forth. So finally, how can we retrieve the kubeconfig? So keep in mind that you can do that, retrieving the kubeconfig using, I don't know, you could use the secrets managed by Kubernetes, or rather clusterctl get kubeconfig copy quick start and exporting here. So once we got this file, you will see here that this file is a valid kubeconfig that is going to be connected to the available IP of the control plane. So what you have to do is to export this kubeconfig tmp copy quick start, and now what I can issue is kubectl get nodes. And as you can see here, we got just the worker nodes. It's like EKS or AKS, so it means that essentially we don't have the control plane. The control plane is externally managed by Kamaji, so we just need to get our worker nodes up and running, install our CNI like Calico, and we are going to see that all our deployments are going to be created. So now we just need to issue kubectl get pods in all namespaces in watch mode, and you will see here that kubeproxy, CoreDNS, and also Calico nodes are going to be up and running. Keep in mind that right now I'm just using Calico because I know that it's working. You can use whatever you want as CNI, Cilium or Flanell, and so on and so forth. As you can see here, the nodes are going to be marked as ready because new pods are going to be deployed there. In fact, if I issue here in the copy quick start kubebird kubectl get nodes, now the nodes are ready. And also here, as you can see here in the describe of copy, we see that essentially the cluster is ready and has been provisioned. So the question is, can we run thousands of clusters with this approach? And spoiler alert, the answer is yes. So what we did at Classics is to benchmark our own solutions. And what we did was to run 1,000 of control planes on AWS. What you can do is to use Cluster API, but keep in mind that this test was done just to be sure that Kamaji was able to manage such a huge fleet of control planes. And these are the infrastructure requirements that we needed. So some node pool for the infrastructure where we were installing etcd, then also the workload node pool that was used to deploy the tenant control plane pods, and another node pool just for the monitoring because Prometheus was consuming a lot of resources. We are going to see that. And about that, keep in mind that we are using etcd to share the data between multiple control planes. So we were just using etcd for the sake of simplicity, although we could have used PostgreSQL, and we started sharding. I know that sharding sounds very bad, but in the end, somewhere you need to shard because it's a matter of pros and cons. The idea here is to say, let's shift the multi-tenancy on the etcd multi-tenant capabilities. So it means that we were using 100 of tenant control planes per each namespace, using one etcd for these 100 of tenant control planes. But keep in mind that what you can do is to use one-on-one relationship between tenant control plane and etcd, but obviously you're going to consume more resources. And also to avoid latency about storage, because etcd is really not opinionated but really sensitive to that, we use the local path provisioner. So we started monitoring etcd, and you see here that the metrics are pretty interesting. You know, I was a site reliability engineer besides being a software engineer, so I really love seeing Grafana dashboards, and this is the dashboard while we were monitoring the first shard of the etcd. So you see here that we got plenty of keys, but the latency was pretty good. And you see here the increase of etcd keys because we were creating the tenant control planes in a batch mode. So creating the first batch, the second batch, and the third batch, just to be sure to avoid, issues with the network. And also the DB size was pretty good. Keep in mind that with etcd you got a huge limit, that is the 8 GB storage. But as you can see here, just the provisioning of the cluster is not consuming so much data. Obviously, when you got nodes, custom resource definition installed, and all the objects, this size is going to be increased. But keep in mind that Kamaji is able to migrate data from one etcd to another one. So it's up to you to what you can do. And also the complet rate, the snapshot duration, everything was working pretty well. You see here that essentially we were able to create 100 of control planes in just 15 minutes, so it was pretty good. And also about the network, you see here that we got some spikes, but that's okay, because in the end we got the clusters that are going to be provisioned. So at the first startup we are creating plenty of objects into etcd. But let's talk about Kamaji, because that's the real game changer here, because it's creating all these objects and orchestrating everything. So this is the overall dashboard when we were running Kamaji throughout our tests. So we started on 7 p.m. and we completed at 8 p.m. So in an hour we were able to create a thousand of control planes. And you see here that the cluster was pretty huge, because we were running a huge fleet of nodes on AWS, and this is the average usage of the CPU. But I would like to show you how it was really cumbersome, the network. So since we were running 1,000 of control planes, the network pressure was pretty important. I wouldn't say terrific, but pretty important, because we were talking about 200 megabytes per second. Obviously, because we got the control planes, the worker nodes communicating each other, and also with etcd. And I want to focus also on the CPU usage. You see here that every time you see a spike, there is the reconciliation, the creation of new control planes, because we need to create the certificate authority, the API server certificates. So all the tasks that you have to do on your own, essentially, these are done by Kamaji. And as you can see here, essentially, the CPU and also the memory usage is not so much. In the end, we were running with 8 gigabytes of memory for 1,000 of control planes. So it's really cheap. So in the end, what we discovered is that if you're planning to run Kubernetes at scale with Kamaji, and then even also with Cluster API, the first thing is that sharding is required, because getting to infinity, I know that is pretty impossible. And you need to automate everything, and as well you need rock solid hardware and trying to fine tune everything. I didn't share here, but I had to increase the reconciliation concurrency in Kamaji, and you saw also that I'm using different hardware according to the node pools. So for the infrastructure we were using more memory offering instances, rather for the control planes more CPU. So you need to orchestrate that in a proper way, and you need to do testing. But the financial takeaway are really impressive, because with AWS essentially you can spin up 1,000 of control planes using EKS, and you can spend up 75k per month. With Kamaji, instead, with these virtual machines that are the management cluster, and these are not reserved instances, we were able to spend just between inverted commas 23k per month, with a huge saving. We are talking about barely 70% of saving. And furthermore, with Kamaji, essentially you can have also a scale to zero, so a sort of sleep mode, because the control plane is running as a deployment here. So what you have to do is just to issue kubectl scale 10 control plane. It was copy quick start keep version replicas to 0. Obviously you need to scale down also the worker nodes, but you're getting the point. Essentially it's like a regular application on Kubernetes. So the answer to this question, it really depends, But keep in mind that Kamaji has been designed to solve the issues for those who are running Kubernetes at scale, and this scale happens sometimes in the data center, so on premises. But if you're working in an organization that is managing Kubernetes on behalf of third parties, so you're a cloud service provider or a managed service provider, Kamaji can be a perfect fit. Or at the same time, if your organization is pretty huge and big, so you got plenty of developers, plenty of teams, and these are looking for their own Kubernetes clusters without the burden of managing control plane, Kamaji can be your life changer, lifesaver, because essentially you are flooding everything. It's like having a team of strategic engineers inside your cluster doing everything on your own. So with that said, I completed my presentation. Remember that Kamaji is open source, so if you can give a star, it would be absolutely great. We got also a channel in this Kubernetes Slack workspace. You just need to look for Kamaji. You can send us an email if you need further information, or rather you can check out our videos on the Classics YouTube channel and all the projects on GitHub. And keep in mind that since we are the leaders in multi-tenancy, according to us, we got also this nice meetup where we are organizing events about multi-tenancy. And with that said, we can open the question and answer session. Muchas gracias.
Okay, Victor Morales is saying this is an interesting approach. In NIFI project, we are using cluster API to deploy the 5G clusters, but maybe having the control planners near to the management cluster can facilitate the closed loop automation process.
Yeah, it really depends. Also, keep in mind that it's an interesting approach, and we see that this is used mostly by on-prem solutions. But yeah, I never heard about Napier project.
Okay. Besides of that, we don't have any other question, I think. Así
No
que,
questions so far.
no. Muy bien, entonces creo que, dado que no hay ninguna pregunta, damos por finalizada esta conferencia. En nombre de todos nosotros, queremos expresar mi más sincero agradecimiento por haber formado parte de esta emocionante conferencia sobre KubeInception, Running Up to a Thousand Cluster in Real World, a Real Cloud Native Wave. Espero que hayan encontrado las charlas y discusiones tanto informativas como inspiradoras. Un agradecimiento especial va para nuestro ponente Dario Tranchitella por compartir su experiencia y conocimientos en el fascinante mundo del KubeInception y la administración de clústeres a gran escala en la nube. Muchas gracias, Dario.
Muchas gracias. Hasta luego.